So more horizontal circles. What was the main horizontal circle we looked at last day? Car going around a corner. And I think in that one we said the best free body diagram was to do a front view, and then friction was what was pushing you in a circle. Here's another nice horizontal circle, artificial gravity. One method of generating artificial gravity in outer space would be to build a circular space station and spin it. You've probably seen it in sci-fi movies, a spinning space station to do artificial gravity. Would that work? Well, let's find out. So here's a side view, here's a top view. Part A says this: if this space station has a radius of 35 meters, what does the period of rotation need to be for an astronaut to experience 80% of Earth's gravitational field? Kiana, what does this want me to find? What symbol is the period? Okay, put it away, and how about putting it in the sink? There you go. Now you're not distracted. What symbol do I use for period? Okay, capital T. So I already know I'm going to be using the 4 pi squared r over t squared version. All right. Any suggestions on how I might want to start out? Really? What? I think a free body diagram. I could use either of these pictures. I think I'll use the top view. So what are the forces acting on this astronaut? No gravity. I was going to start drawing in mg. No. Okay. Yeah.
Isn't there technical gravity?
Let's pretend right now we're far enough away from any planets where there is no gravitational field. So Spencer asked, isn't there technically gravity? Yes and no. It depends on what type of situations you're talking about. But for now, let's say we're doing interstellar space travel, and any effects, by there, the biggest source of gravity would be stars, and you're far enough from the sun that meh. Okay? Okay. What path is this astronaut tracing out? Where must there be an unbalanced force pointing then? Toward the... I mean, I know there's got to be a force pointing there. Is that FC? Does FC ever show up on my free body diagrams? No, so don't put that there. What force is that? What? Man, what, Manny? Normal force. Is that a surface pushing up through the... Yeah, turns out that. In fact, for a rotating or spinning space station, it seems to me normal force is what's pushing us in a circle. And I think, Kiana, you already pointed out for the circle part, we're going to use 4 pi squared r over t squared. Can anybody see the silly mistake I made? F equals what? ma. It's very tempting to forget to put the m in front, to think, oh, that must be the force. No, that's the acceleration. That's the force. I don't know the normal force. Or do I? Manraj, what? 80% of Earth's gravitational field. What's your normal? mg. So 0.8 mg. Could little kids and grown-ups live on this space station okay? How do you know? Well, that's kind of cool. Pause for a second. So as far as I'm concerned, this question has 1, 2, 3, 4 variables, and I can give you any 3. So I can give you G, R, and T and say what percentage? Find the number in front. I can give you the percentage G and R, say find T, which is what we're doing, I think, in this question. But as far as I'm concerned, for a rotating space station, any one of those is fair game. What am I trying to get by itself here? Period. T. Where is the T right now? Yeah. Hey, wait a minute. Is this 1 fraction equals 1 fraction? Stuff moves diagonally. So as far as I'm concerned, the t squared moves to the top, the 0.8 g moves to the bottom, and I end up with t squared equals 4 pi squared r over 0.8 g. Darn right, we square root. So let's plug in our numbers. 4 pi squared times 35 divided by 0.8 times 9.8. This one is absolutely worth trying on your calculator, making sure you can type this in. If you don't have a calculator here, now would be the time to sheepishly fess up and power off your smartphone. Calculator here? This would be a good thing to try typing into your calculator. Mr. Dewick says, strongly hinting. I got 13.27565.
As did I.
So I'll write 13.3, but I'll just store this on my calculator. What are the units for period? Seconds. Ah, I wondered. B. What's B asking me to find? Frequency. Normally, I actually talk about frequency in lesson 1, the kinematics of circular motion, because another way to measure how fast you're moving in a circle is to measure the frequency. I'm not going to put this on a test. This is purely for nerd trivia, but for what it's worth, frequency, symbol lowercase f, is the reciprocal of the period. In other words, if it takes 5 seconds to go around once, the frequency is 1 over 5, or 0.2. If it takes 10 seconds to go around once, the frequency is 1 over 10. It's the reciprocal. And by the way, now you may notice all of your calculators actually have a reciprocal button, a little x to the -1 button. If you press that, it will just find the reciprocal of this answer, and you get a frequency of 0.0753. And frequency is measured in hertz. And that's really the only reason I'm covering that, is because probably if you're a techie nerd, you've heard terms like megahertz or gigahertz when they're talking about cell phone networks or Wi-Fi signals or something. That's telling you the frequency. Okay? So I'm not going to ask you a frequency question on your test. There might be one in the homework, but I think I removed them all. I can't remember. Yeah. Where's the reciprocal button on that one? Let me see. Right next to the constant. So near the very top row, just to the bottom right of the arrows, there's a little x to the -1 button.
It also be x to the exclamation mark?
Nope. That's factorial.
Oh, yeah.
Okay. Now, if you can't find that button, by the way, the low-tech way, and we're going to do this, if you can't find the reciprocal button, you can always go 1 divided by answer button. Could you all do that so that you have the 13.2756 back? Because that's what we're going to use in the next question. So if you don't have if you still have the 13.56 displayed, you're good, but or the 13.26 displayed, you're good, but otherwise 2756, whatever it is, get it back. Okay. Because B, you can almost, if you want to, you could almost cross that out and say not on the test, or you can write a little note next to it, not on the test. But for what it's worth, frequency is the reciprocal of the period, and frequency we measure in hertz or megahertz or kilohertz or gigahertz or whatever. Yeah.
That should be 1 divided by 13.3.
1 divided by answer button, which won't quite be 13.3. It'll be 13.2756, that.
So they got to measure way off.
Number 3. Suppose the astronaut begins to climb a ladder that leads to the center of the space station. If they start to climb a ladder, what will happen to their weight? Gets lower. At what radius will the astronaut feel 30% of his weight or her weight? Parker, what's this question asked me to find? Okay. I think it's going to be the same free body diagram in that I think we're still going to say normal force is what's pushing me in a circle. And I think it's still going to be m 4 pi squared r over t squared. MAC. But how big do I want the normal force to be this time?
30%.
So, what will that? 0.3 mg. What am I trying to get by itself here? Okay, I think times the t squared to the top and divide the 4 pi squared because stuff moves diagonally. So I think I'll have this r equals 0.3 g t squared all divided by 4 pi squared r. Why would I put the r there, Mr. Dewick? I want to leave it where it is. Good, I'm glad you all caught that. That was silly. Do I need to square root or anything here? Nope. I'm going to use my answer button for the t, so I'm going to write 0.3 times 9.8. I'm going to write 13.3, but I'm going answer button. Don't forget the squared, Mr. Dewick. Divided by 4 pi squared. And again, all of you should try typing these in because you might find, especially some of your software, might deal with the pi squared weirdly. Trust me. And I get, worked out actually to a non-repeating decimal, exactly 13.125 if I used my answer button. So 13.1. So would this, yeah. Don't clear your calculator, hang on. Kids ask us, okay, Mr. Dewick, and this is good in theory. Would this work? Could you build a space station of radius, let's say 35 meters? So 35 meters, my room is very roughly 10 meters long, so about 3.5 times as long as my room. Would that work if we built a space station that big and started to spin it? Yes and no. The problem is, if I'm standing, I'm roughly 2 meters tall, a little less than that, but that's a substantial portion of that 35 meters. I would actually feel and probably be able to notice that fake G on my head was different from fake G on my feet. And so I would always, until I got used to it, probably feel like I was about to fall backwards or fall forwards. It would just feel weird. You don't notice it because on the Earth, when you stand up, it is true that gravity on your head is slightly less than gravity on your feet, but your height is such a small percentage of the Earth's overall radius that it's negligible. But your height would be enough of a percentage of a 35-meter radius that probably until you got used to it, you would notice it. Also, that would mean probably technically, because G from head level would be slightly different for G at foot level, objects wouldn't quite fall in a perfectly straight line or with a constant acceleration. There would be an ever so slight increase in speed. So if you had really, really sensitive machinery or really, really accurate instruments, you'd have to somehow take that into account. So would it work? Ish, yeah. But there's a few really obscure stuff we'd have to think about. Parker, you had a question.
If you're in the middle, so it'd just be 0 G.
What will the force of gravity be at the center of the space station? So if we do someday build huge rotating space stations, let's say 1 kilometer across, and we get them spinning, at the dead center along the axis, there would be a 0 G section where you could do research. But a few meters away from that, G might only be not 9.8, it might be 0.1 or 0.2, where there's technically a little bit of gravity, but you might be able to, for example, strap on fake wings and fly. You could do, if we do ever build city-sized space stations and spin them, there's some really neat recreational stuff that could occur in microgravity. Not zero gravity, still a little bit, but enough that, yeah, you could do a lot of neat stuff, I think. I hope that happens in your lifetime. So, one nice example of horizontal circles, artificial gravity in outer space, but we can kind of do something similar on Earth with a ride called the Gravitron. I like example 2. Example 2 is a nice question. Oh, heck, I'll just tell you, this will be the funnest test of the year, because one of the written questions, you're going to go on a roller coaster. One of the written questions, you're going to go on a Ferris wheel. And one of the written questions, you're going to go on the Gravitron. And then one more written question, you're either going to be in a space station or on a race car going around a corner. You should be paying money to write this test, because it's going to be just fun. How many of you have been on the Gravitron? What is the Gravitron? That's the one that goes in a circle. There's 2 types. It goes in a circle really fast, and then either the floor drops away from your feet and you're suspended, or the room tilts up at 90 degrees. Okay? We're going to look at the one that stays horizontal, because that's a little easier physics. By the way, if the room tilts up at 90 degrees, that's the same physics as the roller coaster loop, which we've done already. It's a vertical circle. The Gravitron spins its riders around in a circle. If the ride has a radius of 4.8 meters, and it rotates every 2.5 seconds. Ooh. Annika, what's A want me to find? What's that? What symbol? Hey, what's mu? I don't know. What's mu with you? Okay. Any suggestions on how we might want to start? I think so. Again, as soon as there's a mu, means there's more than one force. So they gave me a picture, Annika. Let's do the picture right here. What are the forces acting on this person? Are we back on Earth? Get the obvious one. Okay? Hang on, slow down. Is this person sliding down the wall?
No.
Are they sliding up the wall? So in the vertical direction, forces must be, I'm looking for where they start. So I know there's an arrow the same size as gravity. I'm not quite convinced that I know what it is. I think I do, but let me just make a note to myself, come back to that. Keep going. What path is this person tracing out? Where must there be a winning unbalanced force pointing then? So I know there's also a force that way. What force is that one? How do you know?
Because it's pushing off.
It's a surface pushing. Okay, so if that's the normal force, anybody want to make a guess as to what that vertical force is?
Friction.
That's friction. It's a little weird, we're not used to it, but in this case, friction is pointing up. Okay. What path, Deegan, are we tracing out? Got you mid-yawn. Deegan, what path are we tracing out? Looking for it that starts with the letter C? Don't look in your notes. What path are we tracing out? I'm looking for a word that starts with letter C. Where must my winning force be pointing? Toward the? Who's winning? Who's losing? It's a trick question. No one. Okay? So what I have here, actually very similar to the space station, the normal force is what's pushing me in a circle. Am I going to use the v squared over r, or am I going to use the 4 pi squared r over t squared? And how do I know? How do I know? 2.5 seconds. If they had said, given me the speed, I would use v squared over r. So Deegan, are you okay? My next line is going to be m4 pi squared r over t squared. That equals the normal force. I don't know the normal force. And unfortunately, I can't say, oh, but look, because there's nothing pointing that way. I don't know another force the same size as the normal force. Okay, we pause there. Are we sliding downwards? Are we sliding upwards? Vertically, that's also an equation. What's my vertical force equation? Yeah, Parker.
If we're finding the coefficient of friction, if friction and gravity are balanced, just speed up that way.
If they're balanced, what can I write as an equation? Because this is the aha moment right here.
Mg equals friction.
What?
Mg equals friction.
Let's write that down. Okay. We get two equations, a horizontal circular one and a vertical one. Friction is what times what?
U times rho.
So I can write this as mg equals mu times the normal force. Get the normal force by itself in this equation. So you ready? I'm going to walk back over here and I'm going to say, I don't know the normal force. Oh, but look, 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 look. I know something else that's the same size as the normal force. What? Mg over mu, not mu mg. In this case, it's mg over mu. A little different. So I can walk this to there. I can say mg over mu equals m 4 pi squared r over t squared. Can little kids and grown-ups go on this ride?
Yes.
Will someone heavier and someone lighter be able to go on this ride?
Oh, what did it say?
So will they be able to go on this ride?
Yes, masses cancel.
Okay. If you look up for a second, as far as I'm concerned, there is G1, mu2, R3, G4. There's 4 variables. And I can give you any 3. Find the 4th. I'll spoil it. I'll say I've never asked someone to find G on a fake planet. I've never given like, here's some numbers. What fake planet are we on? What's G on the mystery planet? I could. So really though, I'm going to ask you to either find mu or R or T. Or if instead of the 4 pi squared R over T squared, if we have V squared over R, I'll be asking you to find mu or V or R. Give you any 2, find the 3rd. What are we trying to find here, Annika? Stuff moves diagonally. The mu is going to move to the top. The 4 pi squared r is going to move to the bottom. T squared moves to the top next to the g. Right? Stuff moves like that. Is that okay? I'm saying that's going to go there, that's going to go there, and this whole mess is going to go there. We're going to get gt squared over 4 pi squared r. That equals mu. Now we'll find out if I made up decent numbers. I was trying to make this realistic. 9.8. What was the period? 2.5? Kiana, what don't I want to forget? There you go. All over 4 pi squared. And then R was, what, 4.8? What do you get? By the way, this is one of the ones I'd love you all to try. Some of you may find that you have to, after the pi squared, you have to put a times sign. You can't just put a number. Some of you might be able to, but some of you will get an error. So that's one of the reasons I'm having you try typing these in. 0.323. Now that's the minimum coefficient of friction. So probably what they would do is they would have fairly, let's say, rough carpet there. And on the fabric of your clothing, that would be enough of a mu and give you some extra probably. Okay? Yeah, Parker, stuff moves diagonally when you have one fraction equals one fraction. So anything on the bottom moves to the top on the other side of the equal sign. Anything on the top moves to the bottom on the other side of the equal sign. Ooh, what's B want me to find? Centripetal speed? How could I find speed? Sorry? Okay, don't write this down. You absolutely don't write this down. Could go, oh, okay. Normal force equals mv squared over r. And you could absolutely then go mg over mu. That totally works. But what's this asking me to find?
FC.
Not FC. That's not force. What? Is there an equation for VC on your formula sheet already? Did they tell me R in the question? Did they tell me the period in the question? I'd do it this way. You'd get the same answer if you did it with Manraj's suggestion, but I'm going to argue this is a little better. This is a little better. 2 pi times 4.8 divided by 2.5. Remember, this is just distance over time in disguise. The circumference is the distance, and the period is the time. 2 pi times 4.8 divided by 2.5. And I get a centripetal speed of 12.1 meters per second. So I like gravitrons, I like gravitrons, I like gravitrons. Gravitrons are a nice question. To my shame, until about 4 years ago, I would always, right around now, tell students I'd never been on the Gravitron. And the reason was, when you go, I'd take the kids to Playland in May. I would go every year. The P&E owns the Gravitron, not Playland. And so it wasn't part of Playland's usual infrastructure. But then about 4 years ago, Playland had several rides that were shut down for repairs. And so the P&E loaned them the Gravitron, and I finally went on it. If I was a billionaire, I would love to buy a Gravitron and do some really, really fun experiments in it. For starters, I would love to try playing catch. If Shay was across the room from me in a Gravitron, I would love to try playing catch. The other one that would be fun, Shay, is if we each had a super soaker, if we tried to spray each other, I think we would find, remember the Coriolis video that I showed you? We would find everything appeared as though it was traveling in an arc. In fact, if I wanted to spray you, I would have to aim at Francesca and it would arc all the way over and get to you. There's a whole bunch of neat experiments that we could do. I think that would be a lot of fun to try. So Parker wants to see the photo. Oh, wrong unit, Mr. Duke. So here's someone riding the Gravitron, okay? But I'll also say what he's feeling right now is a slightly different fake gravity on his head than he is on his feet. If he rode this for a while, his inner ear would probably get a little bit befuddled. And it's amazing how fast it can happen, but also your body will adapt as well. Put your pencils down, look up.
You jump there?
Yes and no. I'll answer your question in a second, just hang on.
Last video, I was at the Ashton Graybiel Spatial Orientation Lab at Brandeis University, and while I was there, one of the team just casually mentioned that they have an artificial gravity laboratory.
Artificial gravity facility sounds like something out of science fiction. But it's not science fiction. Very much a reason why I'm keeping my head straight. This is the artificial gravity facility, otherwise known as the rotating gravity facility. Let's do some experiments. This is unscripted. I don't know what's going to happen now. Things are going very weird when I move my arms.
Okay, this is more realistic to what an artificial gravity space station might be like. And you're going to see there's some genuine issues that we have to take into account that sci-fi movies
Okay, so
over.
it's a room
Okay.
that rotates. No one has invented science fiction gravity generators yet. But if you have a theoretical spaceship going to Mars and you want to generate apparent gravity to keep astronauts healthy, that's what you do. You would spin up the ship and use centrifugal force. And that lab is the research prototype. How do humans deal with a very strange gravitational environment?
The first thing that you should do is try to push yourself off the wall and align your body with the direction of the result.
Okay.
Unlike our space station that we did, there is gravity here. So if you add normal force plus gravity tip to tail, the resultant is at about not quite a 45-degree angle, but that's where he's feeling straight down right now. Okay, so he's got to have his eyes are telling him straight down is completely different from what his inner ear is telling him. And that's going to lead to some weird effects.
Now you're standing upright.
Wow.
Now you're standing upright.
Walk or something?
No, don't walk. A little dangerous. No, don't walk. A little dangerous.
You asked, could you jump it? It would be dangerous until you got very used to it. You would almost certainly take a pretty nasty wipeout when you landed. Your body just wouldn't know how to handle all the differences.
It is almost impossible to envision long-duration space flight without artificial gravity. The best way to study artificial gravity on Earth is to build a rotating environment. We started designing it in the mid-80s. Ideally, we want to study its effects on the human body, and we want to learn also how to pre-adapt astronauts to the force of artificial gravity.
So now it's going to get weird.
99.9%, those will be highly dysfunctional individuals until adapted.
They have NASA standard sick bags for everyone, by the way. I was required to keep one in my back pocket throughout, just in case. Because if you tilt your head too fast, your inner ear has no idea what's going on, and things go wrong and very quickly.
You now move your arm and try to go as straight as you can. Move your arm and try to go as straight as you can.
He told his brain, lift your arm straight up. They did that.
Oh, I moved my head.
Okay?
You shouldn't move your head.
Do you get used to this?
Yeah, you move your head.
Do you get used to this?
Yeah, move your arms and try to feel this force that is. And try to feel this force that is.
Okay, just to be clear, I'm not putting this on. As far as I'm concerned, I'm not putting this on. The signals I'm giving to my muscles, I'll move my arms forward.
So one basic issue would be, initially, until you got used to this, you would be very clumsy. Do we want our astronauts being very clumsy when they're at the controls of a space? This is something we'd have to somehow take into account. We would have to build some kind of an acclimatization procedure to get used to this. So now you can see his arms are going straight. He's having to make an effort. He's having to push his arms to make them go straight. But watch, it gets even weirder.
I'm forcing them. I'm pushing against a force.
If you keep going, at some point, if you keep going, you won't feel the force at some point. You won't feel the force anymore. That's weird, right?
Oh, that's so weird.
That's weird, right?
That's so weird.
You saw his face change. His brain has just now adjusted. Even though he is pushing against that inertia, his brain doesn't feel it anymore. Now his brain has told him that's what you do to raise your arms straight, and he can't feel it anymore. You saw, oh, that's weird. It just vanished. Yeah.
So when he gets out of it, will he?
We're going to find out. Good. Hold that thought.
So now you are
We're doing some
adapted.
Good predictions here.
So if I try to do anything else, I haven't adjusted. So if I try to do anything else, I haven't adjusted to. My body's got used to.
That's right.
My body's got
Wow. That's right. One way to visualize this force is for me to try and throw a little tennis ball at you. I will throw a little tennis ball at you. I will.
Let me emphasize, it's not a force, it's inertia. There is no extra force. But this is how weird it would
throw
be
it
in a
straight at
rotating
you
body.
and see what happens, okay? Throw it straight at you and see what happens, okay?
What? Whoa! I'm struggling to work this out because in my head, this is a normal reference frame. In my head, this is a normal reference frame.
And now I'm gonna throw it over there.
Yeah.
And now I'm gonna throw it over there.
Okay.
And
Are you ready?
hopefully
Yeah,
it's
ready.
gonna get at you.
Okay.
Are you ready?
Yeah, right. Yes!
Oh, nice.
Yes!
Oh, nice.
This is why I would love to have super soakers on the Gravitron, because I think you would have to aim way off to the side and it would arc.
Great!
All those odd effects are from the Coriolis Force. It's not a real force.
Coriolis Force. It's not a real force.
That's why I called it the Coriolis
On the
effect.
ball,
It's
but
not a force.
it looks
not a
like
Newton.
one when you're in that
on the ball,
weird
but
rotating
it looks
environment.
like one when you're in that
Have a
weird
look at this
rotating environment.
360-degree
Have a look
image
at
of the
this
lab. Now, it's a little
360-degree
distorted
image
because it's
of
from
the
a
lab.
single camera in the
It's a little
middle,
distorted
but
because it's from a
it's close
single
enough.
camera in the middle.
Here's the
but
tricky part.
It's
The
close enough.
circumference of a
Here's the
circle
tricky
is
part.
longer
The
the further
circumference
out
of a
you go from
circle
the
is
middle.
longer
But because
the further
everything
out
in
you
that
go from the
circle
middle.
is
But
rotating at the
because
same
everything
speed
in that
once
circle
around every
is
6
rotating at the
seconds.
same speed
Things on
once
the
around
outside
every
have
6
farther to
seconds.
travel.
Things
So
on the
they're moving
outside
at a
have
faster
farther to
speed
travel.
than things
So
on the
they're moving at a
inside.
faster
On the
speed
outside, we're moving
than
pretty
things
fast, but
on the
that camera
inside.
in the middle
On the outside,
is
we're
just
moving pretty
spinning on the
fast, but that
spot.
camera in the middle
So let's
is just
mark the
spinning on the
sideways
spot.
speed that
So
everything
let's
is
mark
moving at
the
relative to the
sideways
rest of the
speed
world.
that everything
Green
is
is
moving
fast,
at relative
red
to
is
the rest
slow.
of the world.
When
Green
you
is
throw a
fast,
ball
red is
across that
slow.
room, it keeps that sideways speed that it had when it left your hand as it travels into slower moving areas of the room. Now out at the edge that was fine, it was going the same speed as everything around it, so it was like it aimed for the centre. But by the time it starts to get there, it's a missile flying outwards compared to everything around it. Now from the outside that makes sense, after it leaves your hand, the ball just moves in a straight line. From the inside, it looks like there's a force suddenly sending it sideways, and that is the Coriolis Force. And it's not something your brain has evolved to deal with.
Now, if you move your arm, you're pretty much fine. Move your arm. You're pretty much fine. Just by moving around, you've been adapted. Just by moving around, you've been adapted.
That's ridiculous. Thank you so much. I'm going to throw this at you one more time. I'm going to throw this at you one more time.
The question that lab needs to answer is, can humans adapt to that over time? And if so, how long does it take them to come back down to Earth?
How long does it take them to come back down to Earth?
Abby, can you bring us to zero? Bring your hands down. Can you bring us to zero? Bring your hands down and don't move.
I swear the room is... Oh, that's weird.
So try to swing your arms in front of you. Try to swing your arms in front of you.
Now that force, the brain has to readapt. So if astronauts are in a spinning space station, they would have to readapt. Do we want them to be clumsy when they're trying to land their probe on Mars? Probably not. So we would have to think all this through, Rachel. This would have to somehow be built into the mission, because the last thing you want is just before touchdown for an astronaut to reach for that control and grab that control accent. You know, that's bad. So it's much weirder than you realize.
You've been adapted to unusual forces on your arms, but you feel it, right? Unusual forces on your arms, but you feel it. Now you have to readapt. Now you have to readapt.
Thank you so much.
Example 3. The picture below shows a frictionless tabletop in top view. The mass is 4.15 kilograms. It's attached to a 2-meter long string. It's moving at 2.5 meters per second. Write force equations and solve for the string tension. I guess this wants me to find T. Okay. This is a job for a free body diagram. What are the forces acting on it? Get the obvious one. Which way would gravity be? If this is top view, I guess into the page. So I got around that with the car going around the corner last day by drawing a front view. Let's just remember that gravity is going into the page, okay? What else? Let's go systematically. Gravity, what else? Coming out of the page towards us, those cancel. Okay, what else? Tension. So, Kiana, I'll definitely put there. By the way, again, did FC show up on my free body diagram? No, doesn't show up. What path are we tracing out? Who's winning? Who's losing? Equals? Well, we can start up by saying tension is what's pulling us in a circle. Which version of FC am I going to use? The one with the V or the one with the T in it? Okay, so it's going to be mv squared over r, and oh, I think that's all I need, because I know m, I know v, I know r. I can find tension. It's going to be m 4.15, v 2.5, don't forget the squared, all over 2. 4.15 times 2.5 squared over 2. And I get, I guess, 13.0 if I round to 3 sig figs. Newtons. I kind of like that question. But yeah, a little easy. Let's go to a more interesting application. So example 4, same kind of an idea, but now we have an extra, sorry, I'll scroll back, 13.0. Okay. In example 4, instead of having the string attached to a post, we've drilled a hole through the table, and we have a larger mass hanging down. Look up, I'll show you what the setup is like. So here's my own version of this. I've got a mass hanging on the end of this red ball, and here, this hand, with my right hand on your left, this is where the table is. First of all, you can see if I just let it go, gravity pulls it down. But I can spin this, and I can find an equilibrium point. If I go a little slower, you're going to see the mass start to go down lower. And if I go faster, I can raise the mass up. But there's a balancing point. Now, this is without the table, and if you're looking really, really close, you might notice that this string is actually at an angle. Did I say angle? I don't want to do the component version. We could. I'm not going to bother doing the component version. Instead, I'm going to say, imagine that the spinning mass is on a nice flat horizontal surface like a table. Faster you spin it or the slower you spin it, you can control the forces here, the equilibrium. So, first of all, what does example 4 want me to find? I think I'm going to use the one with the V in it, not the T. This is a job for a free body diagram. What are the forces acting on big M? Get the obvious one. I'm going to call that big M G, because it's the larger mass.
Big F.
What else?
Tension.
I think tension, isn't it a rope? No normal force here. I think tension. I think those are the only two forces acting on big M. What are the forces acting on little m? Get the obvious one. Well, we have little mg. We have normal force. What path is little m tracing out? A circle. Where must there be an unbalanced force pointing? Toward the... Okay. What's my equation? Who's winning? They want me to find the speed of little m, so I'm just going to write an equation for little m. Who's winning? Who's losing? It's a trick question. In fact, I think it's the same equation we just did. Its tension is what's pulling me in a circle. In fact, tension is going to be little m, and I'll use the v squared over r because they gave me, they asked for speed. If they had asked for the period, I would have put the 4 pi squared r over t squared in. I don't know tension. Or do I? Let's write an equation for the big mass. Is the big mass accelerating down? Is the big mass accelerating up?
Tension is the same as mg, isn't it?
Which, I got two m's.
Big mg.
I can say over here, tension also equals big mg, and I can walk big mg right to there. That's the aha moment here too. Kind of like we did with friction and gravity, but not quite as complicated as the Gravitron because there's less stuff to move around. But yeah, Parker, I'm going to get this. Big mg equals little m v squared over r. So in this setup, as far as I'm concerned, there is 1, 2, 3, 4, 5 variables. Big M, little g, v, and r. I can give you any 4, find the 5th. Then you would have this. 4 pi squared r over. Same setup. What are we trying to find though, Manraj? Get the v by itself. I think times the r over. Are we going to get our old friend the square root of GR and some other stuff, but are we getting a square root of GR? We've probably done this right. Probably. So I'm going to get this. Big M GR over little m. I think that equals v square rooted. Okay. V equals the square root of big M, 3.6 times 10 to the negative 2, times 9.8, times what was R, 0.42 meters, all divided by 9 times 10 to the negative 3. Square root of that, 4 point something? 4.06? Is that right, folks? Everyone else agrees, or am I wrong? Seem not? Okay. So that's kind of neat, just because also kids kind of like that little, oh, if you spin it faster, you can make the mass go up and down. I'm not going to give you one where we're going to make big M or little go up and down. You could. I could give you its acceleration. In that case, tension wouldn't be equal to mg. I'd have tension minus mg equals big ma, or mg minus tension equals big ma, depending on whether tension was going up or down. Could totally handle it. Not gonna. Banked corners are cool. And in a normal year, we would cover it, but this year, I'm just going to have to cut corners.
That was a good one.
Sorry? I'll come look in a second, but I want to make sure I get through everything. So you can cross out example 5. You can cross out B. You can cross out example 6. Okay?
You're breaking my heart.
What's your homework? So here's what I assigned my other students. Okay, number 1 is good. 2 is good. 3 is good. 4 is good, 5 is good, but you can skip 6. You can skip 7. You can skip 8. You can skip 9. Just let me get through this. Skip 10, skip 11. 12 is good. Skip 9, 9. So 12 is good. 13 is good. Yep.
They picked in Coriolis, but it's a count when you're like SpaceX science, like.
Oh yeah.
How do they do that?
Good math. We'll talk about that more when we start actually doing rocket science next unit. But for now, if any of you are good machinists and know how to weld, I think this could be a serious moneymaker. This is something some machinists invented just in their shop, and I haven't seen it anywhere else. It's called Centrifury. It's a competitive game. Okay, so here's the object.
All right.
They've basically taken a children's merry-go-round from a playground, they've strengthened it, and they put it on a rotating motor. In the center, there's a button that says winner. Both players are playing against each other. They have to lean forward, and as long as they can hold their finger on the button, they're okay. First person to let go loses.
Object of the game.
Okay?
Object of the game. Don't let go. Here it comes.
I think you could totally make money like the way they have mechanical bulls. If you built a transportable version of this, I'll bet you could probably charge $5 or $10 a game because people would totally like the bragging rights of beating each other. You could soup it up a little bit. You could add a G meter in front on each screen so that when they hit the maximum Gs, a little light goes off and then it starts counting down. How many Gs are they pulling? About 4.3, 60 RPM, that's 60 revolutions per minute. What's the period in seconds? Do the math in your head. If it goes around 60 times a minute, what's the period?
36 seconds.
No. If it goes around 60 times a minute, what's the period? 1 second. So this rotates once a second. Okay, you could even have different periods of rotation. Oh, you want the expert level? We'll rotate every 0.8 seconds, which would increase the G's. You know how most amusement park rides now on the roller coaster, they have a little photo section on one of the hills? You could totally build a photo section in of people straining under the G's, and they could buy that photo when they were done, right? You could, I think, if you're a good machinist, feel free to take this idea. You could make some money from this. Like, wouldn't you pay for that photo when you're straining? You put a little G meter right here that would show the G's increasing until they hit maximum, and then have a little flashing light while you're at maximum. You could time it, and whoever broke like 30 seconds gets a free ride or something. You could do all sorts of neat stuff, I think. So that one's kind of neat. India Wall of Death. Hold your thought. So this is very popular in India at state fairs, but I've seen this, I saw this at the P&E when I was about 8 years old. It's called the Wall of Death. So remember our Gravitron? There, in the Gravitron, you spin the room. Here, you get the velocity, the V from the vehicle itself. Gravity down, friction pointing up. And as long as you're going fast enough to make a big enough normal force, okay. So I have a clear memory, I'm maybe 8 years old, and there's a guy on a motorcycle, and he's doing the same thing that this person in the car is, where he's sitting up on the edge of the motorcycle, like this person here is, holding his hands out. And this tells you how long ago it was. People held out dollar bills, so it was before the loonie, and he would grab the dollar bills, and that's how they made a little tip. Okay. And one more.
I am in an unpowered glider somewhere over Oxfordshire with Bruce, my pilot and instructor behind me. Bruce, thank you very much.
Bruce, thank you very much.
So we're going to talk about something in gliding or in air piloting called the graveyard spiral. Anybody here going for their pilot's license? So this will be one of the things they teach you to be aware of.
Water with me. Now we're in level flight at the moment, so as you'd expect, the water in the bottle is about level. But watch what happens when we start to turn. Bruce, give us a, there we go, a bit of a turn to the left. Bruce, give us a, there we go, that's a heck of a view. Now look at that. Have a look at the horizon line.
Have a look at the horizon line.
Okay, are we turning? But look at the water bottle. It's level with the airplane. The people in the plane right now, they cannot feel that they're turning. To them, gravity is still straight down into the center of the airplane. So imagine you're in a fog bank, okay? And you don't realize that you're turning. When you turn, you also lose altitude. All you see is your altitude is decreasing. So what are you going to do? Pull, which increases the turn. Now you're losing altitude faster. You can't tell that you're turning because you're in a fog bank. So what are you going to do? Pull up. Now that increases the turn even more. Now you're losing altitude even faster. And they call that the graveyard spiral. Many pilots have died because of it.
Massively away from horizontal. But look at this bottle. The water level here is still flat. If you can't see the horizon, then as far as you're concerned, you're not in a turn. We're going round. Now that's very strange, but if you've ever been on a jetliner or an actual commercial aircraft, you'll know that a commercial aircraft can do this kind of turn without slopping your in-flight meal or your drink all over the place. Thank you, Bruce. Let's go back to 11. So what would happen if we couldn't see the horizon? Because there's some really weird sensory illusions that come into effect there. If you lose sight of the horizon and you've been turning for about 15-20 seconds, your ears, balance sensors of your brain, get used to it. The only difference you feel is a little bit of G-force that's really difficult to detect. And if all you've got going is what you think is down, well, the forces are adding up. So down is always going to be towards your feet, even if you're turning. And even a bottle of water or something isn't going to pull you in. So again, as we turn to the right, still straight here. So if we were a little bit higher, if we were under those quite scary clouds above us, we wouldn't know if we were turning, and that's worrying. Because if you turn, you start to lose a little bit of altitude, and if you're starting to descend, if your altimeter says you're going down, and you think you're flying level, then you're going to pull up to try and keep your height together. In a turn, that just makes it worse. That just tightens the turn, and you go into something that is called graveyard spiral. For obvious reasons. That is also the reason that we are not flying in cloud or at night. Yep.
Or at night.
Yep. Oh boy. Yep. Oh boy.
Yep.
Oh boy. Don't freak out. Don't freak out. Don't freak out.
Don't freak out. Don't freak out. Don't freak out.
Oh boy. Oh boy. Oh boy. Oh boy. Oh boy. Oh boy.
Vertical loop.
Bruce, thank you so much!
Bruce, thank you so much!